floor is yours, Chiara.
Okay, great. Thank you so much for the kind introduction, Danielle. And it's a real pleasure to be speaking with you all today. I hope to visit Taiwan in real life at some point. It seems like a really beautiful place. So today I'm going to tell you about the gravitational wave spectrum and then where pulsar timing arrays are on that spectrum and how they work. And then I'll guide you through the new NANOGrav 15-year data results and why we're so excited about them. And after that, I will speculate about future directions that will go in as a collaboration. So NANOGrav as the collaboration has about 200 people in it. So as far as gravitational wave experiments go, it's very small. And so if you have ideas that we haven't considered yet or thought about, please do send me an email because chances are we just don't have expertise in your field. So the gravitational wave spectrum goes from very high frequencies up here where you see the LIGO detector to low frequencies where gravitational waves live. So for many years, LIGO was the only gravitational wave detector to have directly detected gravitational waves. And the LIGO detector can detect solar mass black holes that are, maybe tens of solar masses up to 100 solar masses that are in their final merging phase. So you get a brief signal for a fraction of a second from LIGO in the LIGO band. Now, LISA was just adopted by the European Space Agency, and NASA is a junior partner and is slated to launch in about 2035. And LISA is a mid-range experiment, so it's going to have around millihertz gravitational wave frequencies. And in that range, we expect to see supermassive black hole binaries that are also in their final stages of merging, but now they live in the detector for something like a few weeks, maybe up to a month. And over here at the very low frequency end of the gravitational wave spectrum, we have pulsar timing arrays. And pulsar timing is a nanohertz gravitational wave detector. So a nanohertz is a hard concept to wrap your mind around. So just to give you an example, a nanohertz would have a period of 30 years. And so these are very long gravitational wavelengths. The wavelengths are indeed light years long. And our sources of gravitational waves are also supermassive black holes, but the very massive supermassive black holes. So these ones are 10 to the 8 to 10 to the 9 solar masses. And they're not in their final merger stage. In fact, they're in their very slow in-spiral phase. The signals from these supermassive black holes will stay in the pulsar timing array band or in the NANOGrav experiment for about 25 million years for a typical source. So these are not transient, they're not going anywhere, and they are perfect for doing electromagnetic follow-ups because we have a lot of time to find them. So the in-spiral will eventually lead to a merger, but the merger happens between the pulsar timing array and the LISA experiment. So the ISCO frequency for one of these typical binaries is around 10 to the minus 6 hertz. And that's too low frequency for LISA and too high frequency for pulsar timing arrays. So the strain that we're looking for in pulsar timing array experiments, we thought should be of the order of around 10 to the minus 15. And indeed, the first signal that we found was about 2.4 times 10 to the minus 15. And I just want to drive home the fact that that's about 6 orders of magnitude larger than what LIGO can detect. So these are the strongest gravitational wave signals in the universe, and they happen at very low frequencies. And that's why LIGO can't see pulsar timing array signals. These wavelengths are way too long. So similarly to electromagnetic telescopes, our gravitational wave experiments are purpose-built. We need pulsar timing arrays to look for very long gravitational waves at very low frequencies. We need LISA to find millihertz range gravitational waves. And then we need LIGO and future experiments like the Einstein telescope to look for things that are in the 1 to 1,000 hertz range. Okay, so how does a pulsar timing array work? Well, galaxies have supermassive black holes at their centers, and when galaxies merge, their supermassive black holes should merge. And so here is a tried, tested, and true animation. We've tried to remake it so many times using very up-to-date graphics, and nothing is ever as good. So these are our two supermassive black holes. They are about 10 to the 8 to 10 to the 9 solar masses, and they're in their slow in spiral phase. You can see this 80s space-time fabric rippling out of their merger, going from the galaxy merger where they originate to the Milky Way galaxy where we're timing these millisecond pulsars. And gravitational waves change the proper distances between objects. And so these pulsar pulses will arrive a little bit early or a little bit late as the proper distance between the Earth and the pulsar changes. And that's what makes a pulsar timing array a gravitational wave experiment. So here you can see the signal is being redshifted or blue shifted, and this is equivalent to having your signals arrive a little bit early or a little bit late. Now, if you see that happening in just one pulsar, that could be anything. Our pulsars can have imperfect models, and one pulsar is known to have glitched once. So that's not really saying a lot, but we can't just turn the pulsars on and off again if we think that they're misbehaving. And so if we want to make a confident detection with pulsar timing, it's not enough to see a signal in just one pulsar, but we have to see them in an array of pulsars. And that's why we time currently with NANOGrav 67 millisecond pulsars. And so these 67 pulsars form the 15-year data set. And here you can see something that looks like the DNA of our data set. From the 12.5-year data had an interesting signal in it that was of inconclusive origin, but the 15-year data set, we added 20 more pulsars to. And what I'll show you in the next few slides are the results of adding those pulsars. So the state of the art of the collaboration is that we have 68 millisecond pulsars. We don't use one of them. So one of them is the very first pulsar, that millisecond pulsar that was ever discovered. And it's not actually very good for pulsar timing array experiments, so we don't include it. But we do time it. So we say that we have 68 pulsars, but 67 are good for our experiments. The baselines are anywhere between 3 and 15 years. And we're working on efforts to try to automate things because in the future, we will have hundreds and hundreds of pulsars. But right now, things are done very much by hand. And so in the animation, I showed you a pulsar that was sending its flashes to the Earth. So how can I turn those pulsar flashes into gravitational wave signals? So I'm going to walk you through that right now. So here we have what's called a residual plot of one of our pulsars called J1713 plus 0747. And so what is on the y-axis are the residuals, which is the expected minus the actual arrival times. And you can see that this pulsar has very white residuals. And that means that there's not a lot of structure that's inherently baked into these residuals. And that's great. It's great because a gravitational wave signal would introduce long-term red noise in your pulsars. And so red noise manifests at low frequencies or after a long amount of time. If your pulsar has its own intrinsic noise in it that's so noticeable that you can see it by eye, then it's very hard to distinguish that from something like a gravitational wave signal. And so we can't use those for pulsar timing array experiments. So this pulsar is very good for pulsar timing arrays. You can see at 2012, there was a telescope upgrade that happened. And after that, the signals get even better. They're much more tightly clustered around 0 in terms of their timing residuals. And so we look for the gravitational wave background signal specifically by cross-correlating all of these residuals. So each pulsar will be affected by the gravitational wave background, but each pulsar will also have an independent noise realization. But the noise in the pulsars is not correlated, but the gravitational wave background signal is. And so what we do is that we look at the cross-power spectral density between pulsar A and pulsar B. And when we cross-correlate all of these residuals and all of the pulsars in our pulsar timing array, out pop two things, theoretically. One is this correlation function, gamma AB, and this is a geometric function of the pulsar separation on the sky. And we'll get into that. This is the now famous Hellings and Downs curve. And the second part is the amplitude of the gravitational wave background squared. And that sets the stage for discovering the astrophysics that governs supermassive black hole mergers. And we'll get into that right away. So just to say, the first limits were placed on the gravitational wave background about 30 years ago by Vicky Caspi and her team. And now there are something like 2,300 known pulsars. 10% of them are millisecond pulsars, but there could be tens of thousands of more of them that are detectable. So things like the square kilometer array are going to be really important for finding and adding more pulsars. So Daniel, I haven't been keeping track of hands or anything. I'm just going to count on you to interrupt me when you need to.
Yes, I will. I'm keeping track.
Okay, wonderful. Thank you.
I think everything is clear so far. So
okay, good. So the first target that we're going after is NANOGrav, and indeed our primary target is this gravitational wave background. And so we believe that the gravitational wave background comes from the cosmic merger history of supermassive black holes. Now, again, it's not because we think that there are tons of these. In fact, there might be, but the main contributor to this background is the slow evolution of the supermassive black hole binaries. They evolve so slowly. And for the diehard physicists, you'll know that F dot GW scales as frequency to the 11/3. So at very low frequencies, you're moving really, really slowly. And as you go to higher frequencies, you get this runaway effect that eventually leads you to chirp, and you can make your famous whoop sound. But for supermassive black holes, you get a low frequency hum. It's more like the end of yoga class where everyone gets together and goes om at the same time. And so at the very lowest frequencies, there's this buildup of gravitational wave signals, and there could be hundreds of thousands of these supermassive black holes in each frequency bin. And that makes the signal stochastic or random. So we can't measure the individual supermassive black hole binary signals, but what we do is we measure them in aggregate. We measure the superposition of all of these signals, and the amplitude of this signal can tell us about galaxy evolution and supermassive black hole masses, and we'll get into that. So while we believe supermassive black holes should be sourcing the gravitational wave background, there could be other things that also contribute to the gravitational wave background, such as primordial gravitational waves from quantum fluctuations in the early universe. I will touch on that towards the end of this talk because it's very cool and very exciting, but I'll only have a couple of slides on that. So this, again, gravitational wave background generates a signal that should be in all of the pulsars. And we try to access that signal by cross-correlating all of these pulsar residuals. So when you do this, this search, you get this amplitude of the gravitational wave background, which is defined by the characteristic strain. So the characteristic strain, in turn, is a strong function of your black hole mass and your galaxy merger rates. Because remember that when you're modeling this version of the gravitational wave background, each galaxy has a central supermassive black hole. And when the galaxies merge, their supermassive black hole should merge. And so this amplitude of the background is intrinsically tied to your galaxy merger rates. You can also see that the characteristic strain squared scales as this chirp mass to the 5/3. And the chirp mass is a combination of the mass and the total mass of your binary and the mass ratio. And so things like your empirical scaling relations for black holes and their host galaxies become really important, and scatter in those relationships becomes really important. Really, anything that gives you more massive or less massive black holes becomes very important and indeed observable, because it's really the dominating factor of what sets the amplitude of the gravitational wave background. And in practice, what this means is that the frequency that you expect decouples from the strain equation and comes out into the front. And when you take the square root of this, you can see that your characteristic strain scales like frequency to the -2/3. And so this frequency to the -2/3 is then multiplied by some unknown amplitude. And that amplitude is this double integral up here. So when we found the evidence for the gravitational wave background, we can now in turn place constraints on galaxy merger rates, on the volume that encloses the background, the Z term that we integrate in, and the chirp mass of the black holes, or this integrated mass range in this volume, which is really phenomenal. There's no other way to access these numbers. For anyone who's a cosmologist and would prefer to think about things in terms of omega GW, that's proportional to the characteristic strain squared. So I just want to remind you how these are all related. We cross-correlate our pulsar residuals in this SAB function. This is the cross-power spectral density. Out pops this gravitational wave background amplitude. That's the characteristic strain squared, which I just described up here. Now, the second part is this gamma AB function, which is the Hellings and Downs curve. And before going to the Hellings and Downs curve, there's a few more things that I just want to mention in terms of the underlying astrophysics. So I, of course, made some simplifying assumptions when I said that the characteristic strain scales as frequency to the -2/3. You implicitly assume that your black holes are being driven to merge by gravitational waves and that your binaries are circular. That's the easiest thing to do. So of course, that's the first thing that we do. However, at very low frequencies, when the black holes are just starting to become, bound pairs, they can be driven to merge by other things like gas that's interacting with the binary and stellar hardening effects that help them to get into the gravitational wave emission phase at all. And gas and stars and having eccentric binaries, all of these things are much more efficient to make the binaries merge than just gravitational waves. And so effectively what that does is that it causes a deviation from this F to the -2/3 power law at very low frequencies, which are equivalent to very wide binary separations. So when they're very far away from each other, it's not gravitational wave that's the most efficient mechanism. It's all of these different astrophysical phenomena that are more effective at getting the black holes to merge. But that's only good up to a certain point, right? When the black holes get close enough to each other, then they start emitting gravitational waves effectively, and then they run away and merge. But what that means is that looking for evidence for this turnover at low frequencies can also tell us more things about how the cosmic population of supermassive black holes is merging. So the turnover is in blue, so it's mapped to this blue text here, but there's also other things like galaxy population uncertainties. And so this is the overall amplitude of the gravitational wave background that can get shifted up or down. And so I mentioned before this very strong dependence of the strain on the black hole masses. And so things like your black hole host scaling relations become really important. Other things like merger timescales, how all of these things evolve as a function of redshift, how many galaxies host supermassive black hole binaries, this pair fraction, all of these things will affect the amplitude of the background and scale it up or down. And then the environment will make it turn over or not turn over. It'll make it scale as a power law. So this brings me to the first result, which I think is very interesting. If you look on the right-hand side, this is the first result I'm showing you from the NANOGrav 15-year paper. You have a model that just has supermassive black holes that are only emitting gravitational waves that are fit to the data as a strict power law. It's purple. And then if you look at the best fit model in blue, it kind of looks like it's turning over. But there's not a huge amount of evidence for this. You can squint at it and really convince yourself that either thing is true. And that's because these are the very early days of finding a signal. But what is really exciting is the fact that we can see a difference between the purple line and the blue line. And it'll take a few years to be able to tell if that's a data artifact or if that's some real astrophysics that's manifesting in the strain spectrum. But it's exciting. It's already a slight deviation from what we would have naively expected. There's also some other interesting things that are happening that are visible more in terms of the residual space instead of the characteristic strain space. And you move from one to the other by getting this additional factor of 1 over f cubed. You can maybe look at this spectrum at 16 nanohertz and wonder what on earth is going on here. That is far from blue and purple. So what is going on in the 16 nanohertz frequency bin? That is an excellent question. We do not know the answer to that question. In fact, my graduate student and I took the NANOGrav 15-year data and then rebinned it to the 12.5-year data and then plotted the 12.5-year and the 15-year data on top of each other. And we still found this. So something very interesting is happening at 16 nanohertz. What it is, we don't know yet. But again, it's like the second interesting thing that you find just by making these very simple plots. Okay, so the characteristic strain, you're all now experts in the characteristic strain of the background. Now the Hellings and Downs curve. So when I was telling you about this characteristic strain, it's this amplitude of the gravitational wave background. So why isn't it sufficient to just find some sort of common red noise in your pulsars and say that's the gravitational wave background? Why do you need anything more? Well, there's a lot of other astrophysical phenomena that can induce red noise in your pulsars. For example, the light from your pulsars can be dispersed by the interstellar medium, and it can cause a delay in your very low frequency radio signals. And that can imitate a red noise process that looks a heck of a lot like a gravitational wave. And so we need more proof that what we're seeing is really a gravitational wave and not just some sort of astrophysical noise. And this proof we get from the Hellings and Downs curve. So we know that gravitational waves change distances between objects. And the Hellings and Downs curve is going to tell you if the delays or advances in your pulsars are correlated or anti-correlated. And so this is how it works. If your pulsars are separated by about 20 degrees on the sky, they have a positive correlation, and the correlation value is about 0.3. And so positively correlated means that your pulsar residuals are advanced or delayed in sync, right? They're going up and down together. However, if they're separated by 180 degrees, because your gravitational wave signals are quadrupolar, they're also positively correlated. So they're also bobbing together up and down. But as you get to wider pulsar separations, your pulsar pulses become anti-correlated. So if they're separated by 60 degrees on the sky, it means that one residual will arrive early while the other one arrives late. And so they're anti-correlated like this. One arrives early and the other one arrives late, and so on and so forth. And when you have the limit of an infinite number of pulsar pairs, out pops the blue line, which is the Hellings and Downs curve. And that tells you if pulsar pulses should be positively correlated or negatively correlated, and how strong that correlation is. So we have the strongest correlations for pulsars that are separated by very small angles, and then also when they're closer to 180 degrees separated on the sky. And there's also two crossing points where there's zero correlation, and those are also really interesting. The negative correlations are, again, nothing to be worried about. It just means that one arrives early and the other one arrives late. And then when they're positive, they are arriving early and late in sync. So the Hellings and Downs curve can't be imitated by anything in nature. There's nothing that'll produce a quadrupolar-like shape like this that will correlate and anti-correlate your pulsar pairs. There's a lot of things that'll give you red noise because it's a 15-year-long experiment, and there's pretty much very few things that over 15 years won't give you red noise. But nothing else can give you the shape of the Hellings and Downs curve. And so we really need two parts to detect in this signal to make a credible detection. In the NANOGrav 12.5-year data, we did have this red noise that was present, but we didn't have the Hellings and Downs curve yet. And now we do. So the black line here is the Hellings and Downs curve, and the blue dots and the error bars give you the points that we measured with the NANOGrav 15-year data. There's a few things that I want to mention about the curve. So namely, Hellings and Downs assumed implicitly that the background was isotropic. And at very large distances, of course, it's going to be isotropic. We have the cosmological principle. The universe is homogeneous and isotropic, so why shouldn't the supermassive black holes be? Well, that's because they're astrophysical sources, and they're built up slowly over redshift. And so you have some that are nearby, and as you go further in redshift, you get more and you get more and you get more, and the signal adds up. So the signal doesn't start at redshift 2, and then there's nothing nearby. It's actually slowly built up in redshift slices until you get out to about redshift 2. And so it's impossible that the background is completely isotropic. We also assume that we have the two polarizations, plus and cross, from general relativity. But if you were to have extensions to general relativity, this would also change or be completely modified. And I'll show you a few of those later.
Sorry, Chiara, could you clarify this last statement about the build-up, meaning that it's not isotropic? Because the build-up sounds it's just like some radial dependence in redshift, not angular. So it would still be isotropic for each bin of redshift, or am I missing?
Right, it could be, but we have things like, so you can do arguments where you look at statistically, if you look at two conical sections of the sky, and then look at, how many sources do you see in one direction versus how many sources do you see in another direction. In 2013, they showed that the background should be roughly 20% anisotropic. And this is frequency dependent to a large extent, because at those very low frequencies, when you have hundreds of thousands of sources, it's very, very isotropic. But if you go up to 100 nanohertz, you might only have 5 or 6. And then your background, the stochasticity itself of the background breaks down and things like highly anisotropic.
I see. So in the limit of a large number of sources, that will become isotropic. It's just that they fluctuate at small, rare events or something. Okay, thanks.
Yes, that's right. And it's unclear, and my group is working on this right now, how large-scale structure affects this.
Thanks.
Yes, thank you. So what we're looking at here in this figure are 2,211 pulsar pairs that have been binned. The binning doesn't actually affect anything but the presentation. It's just a mess to look at if you look at 2,000 unbinned pulsar pairs. There's 21 new pulsars with respect to the 12.5-year data set, and 67 pulsars that have timing baselines that are greater than 3 years. And this looks, this looks good, but you probably want to know what the Bayes factors are for the evidence for the gravitational wave background. So this is a fun-looking Bayesogram that I'll walk you through. And you can ask a few Bayesian questions, such as, what's the Bayes factor of having something like just intrinsic pulsar noise versus some sort of common red noise signal that's in all of the pulsars? And so the Bayes factor for that is 10 to the 12. So there's very clearly some sort of red noise that's manifesting in all of the pulsars. This is indisputable. Then you can say, okay, I now believe that there is some sort of low frequency or red noise signal in all of the pulsars. That's the same signal. Does it have the Hellings and Downs correlations? And the answer to that is yes. So if you look at the 5 lowest frequency bins where we have the strongest signal, the Bayes factor for the Hellings and Downs curve is then 165. And if we say we can't just restrict ourselves to the 5 lowest frequency bins, we have to use all of them, then you get a Bayes factor between 2 and 300. Then you can get fancy and then say, what if it's a Hellings and Downs curve and something else that's happening? And right now, it's not worth going into what those other things are. There's really just evidence for the Hellings and Downs curve.
Sorry, can you clarify? So actually, how do I read this number 200? So I'm not from.
Yes.
What should I be comparing this number to get a sense of?
To 1.
To 1.
Yeah. So the odds of this being just common noise or that has this Hellings and Downs correlations, that's 965 to 1.
Oh, I see, like that.
That's what we found. Yeah. So that's good. We think that that's
Yeah.
good. We think that that's credible. Yeah, 226 to 1 as well. And so this, looking at the 5 lowest frequencies, looking at all versus looking at all of the frequencies, let me just remind you of this. You can see very clearly here, if you look at the 5 lowest frequency bins, 1, 2, 3, 4, 5, that there's, this is clearly, there's a signal here. After 5, you can also kind of go down to the further bins, but it looks like you're really white noise dominated. That these violin plots go all the way down to the ground and would go even further if we extended those priors further, right? You can also see it on the right-hand side in terms of characteristic strain. It looks like 1, 2, 3, 4, 5, maybe, and then everything else looks very noisy. And so what we're saying is that if we just count the bins that clearly show the noise, your base factor is almost 1,000 to 1. But even if you include all of the data and say, I have to include even these very noisy bins where maybe I don't even have a signal, then you still have a base factor between 200 and 300 to 1. Now I curse my animations. We'll get there. Okay. So what's next? What can this tell us? Congratulations. We now have evidence for the gravitational wave background. So I guess we should just go home. I'm already at home. So the thing that I think is really exciting now is that I showed you a very scary equation first thing on a Monday morning, and you were all very patient with me. And now you're rewarded by understanding that I did the thing that we said we could do. We found this amplitude of the background, and I said that we could decompose it into the underlying distribution of black hole masses, number density of sources, and redshift that encloses the background. And indeed, that's exactly what we can do. So we find that the minimum black hole mass contributing to the gravitational wave background is about 10 to the 8 solar masses, that the volume that encloses the background goes out to redshift 2.5, and that there are on average about 7 times 10 to the minus 6 supermassive black hole binaries per megaparsec cubed. There's no other way of knowing this. There's no other way of measuring these numbers. And so this is a really beautiful result. The next thing is, of course, looking for the individual supermassive black hole binary systems. And where are they? So Daniel and I were talking a little bit earlier about these individual sources building up to generate the gravitational wave background. But where are those individual sources, right? There should be some that are nearby. There have to be. We know that there are now about 7 times 10 to the minus 6 per megaparsec cubed. So where are they? Well, one of the ways that we can look for them is through electromagnetic observations. So there have been recent suites of simulations over the last 10 years that have shown that supermassive black hole binaries might have periodic optical light curves that trace the binary period. And that would be a huge boost to us in finding the individual sources, because pulsar timing arrays have very poor angular resolution on the sky. So if you were to do a blind all sky search, you might get an area of the sky that's, 50 to 100 square degrees that contains your sources. And that's, a non-trivial fraction of the universe. So if you do a targeted search and follow up galaxies that you believe might host supermassive black hole binaries, you're solving a lot of problems. Not only do you know what the galaxy is because you're looking at it, but we found that by knowing the sky location, you can improve your strain upper limit by a factor of 2. And having both sky location and frequency information of the binary that you would get from this periodic light curve improves your strain sensitivity by an order of magnitude. And so really, I think that what we should be doing, and what I'm working on with my students, is doing targeted searches of these galaxies with this periodic light curves to try to understand if any of them host supermassive black hole binary systems. So what would come after that? Well, we believe that if everything goes well, we should be detecting at least a few, maybe up to 10 of them by the end of the decade. And these individual binaries might induce anisotropy in the gravitational wave background. So what would that look like? So in 2017, I did a suite of simulations using the local universe, and I found that on average nearby, out to 225 megaparsecs, there should be something like 100 supermassive black hole binary systems. But those black hole binaries are just what exist in nature. They're not necessarily detectable. They're just out there emitting nanohertz gravitational waves. And so what would that look like? Well, here I put them on the sky with this blue star indicating the loud source. And then I bended them up and said, what would this look like as a map of the sky? If I were to make a gravitational wave background map, you can still see this blue star as the loud detectable source that shines brightly or is louder than the rest of the sky. Then you can do CMB style, an angular power decomposition of the gravitational wave background, and plot the CL versus C0, C0 being the monopole or the isotropic component of the background versus L. And when you have a loud source, you get the blue curve. When you remove your loud source, so if you get rid of this blue star and you just have a regular, for lack of a better word, anisotropies or individually undetectable anisotropies, you get something that looks a lot more like a CMB style map. You get all of these blotches in the background. And when you look at the angular power distribution of one of those background maps, you get a level of around 20% of anisotropy in the gravitational wave background. And so anisotropy is interesting because if it's really a Poisson style noise, say that it's not following any kind of structure, that is just random, that can be used to constrain the source population. It would go like 1 over the square root of n. It can also tell you maybe beforehand where you should be looking for your loud sources on the sky. And so the Hellings and Downs curve implicitly assumed that the background was isotropic, but what if it's anisotropic? How does that change things? Well, in 2013, I wrote down the solutions to these analytically. So instead of just solving for an isotropic background, I put in a P of omega hat and then decomposed the background on a basis of spherical harmonics and derived these deviations from the Hellings and Downs curve. And so it's no longer just the nice, blue smooth curve, but now you can have dipoles that are in the background. You can have quadrupoles. You can have octopoles. You can have hexadecapoles, which is my favorite thing to say, and so on and so forth. Afterwards, you can also have extensions to GR. So instead of just plus and cross modes, you can, for example, have a breathing mode. And a breathing mode, again, looks completely different in terms of its correlation function than just plus and cross. So the red would be plus and cross, and then green would be a breathing mode. And so a breathing mode would look like this in terms of its correlations on the sky. So plus gives you the plus pattern, and then the cross polarization like this, and then breathing would be in and out like this, moving all of your test masses in a circle that gets a larger radius and then a smaller radius. But you can't have a breathing mode on its own. It's plus and a cross and a breathing mode. And so we'd have to look for this as an extension to general relativity, but not as something that's completely different. So the last 2 slides that I have before going to telescopes and then thanking you all for your time is about new physics. So I'm not an expert in new physics, but I'm very excited about it because if I think, 50 years ago, it wasn't even clear if black holes were real. Kip Thorne and Stephen Hawking had bets on whether or not there were real black holes and if they were nearby and if we would ever see them at all, which is, it sounds completely bananas now, but people didn't know. So we might be in a phase where we think that cosmic strings aren't real or other things aren't real, but like, who knows, right? It could just be that we grew up that way and that's why we think that. So the NANOGrav 15-year results here show us that, the amplitude of the background is large and that's cool. But the spectral index of the gravitational wave background, if we believe it's sourced by supermassive black hole binaries, is 4.33, which is this red line here. And you can see very clearly that in the data, it prefers something like 3.2. And it's almost completely, in terms of the spectral index of the background, and this is equivalent to alpha as minus 2/3, almost completely inconsistent with this blue curve, which is our simulations of the gravitational wave background. And so what's going on? I think no one is ready to throw out supermassive black holes as the primary source of the gravitational wave background. But I think that we're all becoming a little bit flexible in terms of thinking that maybe other things are contributing to the amplitude of the gravitational wave background. Or maybe it's noise, we don't know. But we're certainly thinking that this is very curious. So what else could be sourcing the gravitational wave background? Well, my colleague Kai Schmitz led a team who really wrote a kind of Bible length of new physics. It was 85 to 100 pages. I think it was 85 pages of text and maybe it was 100 pages of citations of a new physics paper on the NANOGrav data. And I'm only going to highlight a few of these results. So you can see that, inflationary gravitational waves, these are the Grishchuk style quantum fluctuations of the early universe, gravitational waves. If you have a model that's only new physics or a model of your new physics plus your supermassive black holes, you can't really tell the difference between them. It doesn't seem to prefer one model to the other. One thing that really stands out are the cosmic superstrings. And I've had to learn about cosmic string models because before now, I think it was just kind of polite to say that they were exotic and that's all that we would say about them. But now it seems like there's a base factor of 100 to 1 for cosmic superstrings, which are like the string theoretical strings that are now the size of the universe and doing all sorts of weird and wonderful things, emitting gravitational waves. So it could be that cosmic strings are a thing, and we'll have to watch this space and see how these results evolve with the next data release and what happens when we combine our data with our international partners. So in order to do that, in order to continue to developing our experiment, we need more telescopes and we need more pulsars. So unfortunately, the Arecibo radio telescope died on December 1st, 2020. I discovered shortly afterwards that it was the postdoc that I just hired, Deborah Good, who was the last one to use Arecibo. And that's how I knew she was ready to become a theorist. She left the telescope. No one else could use it. It was broken. And I welcomed her to computational astrophysics. So since that happened, we restructured the observing program and moved the pulsars that were being observed with Arecibo to the Green Bank telescope. There's now an ultra wideband receiver and plans for future generations of telescope arrays. But what's really going to be important is the square kilometer array. So right now, Meerkat has already had its first data release. It's got about 70 pulsars that it's timed for 2.5 years. And those are going to be really important for detecting the individual supermassive black hole binary systems. So to summarize, I just want to say that, pulsar timing arrays finally have evidence for gravitational wave background. We have the amplitude of the background and the Hellings and Downs correlations. And it's not only NANOGrav, the European pulsar timing array has found evidence for both of those. The Parkes pulsar timing array has as well, as has the Chinese pulsar timing array. So we now have evidence for a gravitational wave background. The local sources we should be able to detect in about 5 years maximum, if we haven't already started to see them manifesting in the data. And depending on how many of them there are, those will induce anisotropy in the gravitational wave background that should be detectable. And then we'll be in the LISA decade. So what's next is really everything. Thank you for your attention.
Thank you, Chiara. And obviously, very nice talk. Just see if I understand this properly. The way I understand it is an individual source, so the one that you say may be detected in the next 5 years. I would have expected an individual binary system is 100% polarized. If you see it edge on, it's linear. If you see it face on, it's circularly polarized. Now, you also point out, for example, that there is some peculiar signal at 16 nanohertz. So if you were to ask the question, well, could the 16 nanohertz just be a nearby source? Has anyone tried doing a polarized template match on it?
I'm going to show you something that's currently being circulated in the, I'm going to show you because it's my students' work. This is going to be submitted to the archive next week. So let me just pull it up here and show you, but that is a great idea. Okay. Okay. So this is the 16 nanohertz bump I was telling you all about. And what we found is that it's really a 2 sigma bump. And in fact, the lowest frequency bin is also 2 sigma beneath where it should be, where we saw like the evidence for the turnover. So we ran thousands of, Monte Carlo realizations and really found that indeed it was very common to see a discrete spectrum that has these bumps in it that come from individual supermassive black hole binary systems. And in fact, if you then say, shouldn't you have seen that in the 12.5-year data and not only in the 15-year data? I mean, that's a reasonable question. So you can then take the 15-year data and rebin it into the 12.5-year ones. And then you find that the 16 nanohertz bin looks identical. Everything else looks kind of different, but this one doesn't. We can then take that excess power that you see in that frequency and say, if that is a supermassive black hole binary system, what would be at that frequency, what's the distance to that binary and what's its mass, assuming that it's just one. It could, of course, be multiple ones. But it turns out that it's, within 2 sigma of quite a few interesting sources, including some of these periodic AGN, and potentially a binary in a nearby galaxy called NGC 3115. Which people have also been studying for recent years, looking for signs of binary activity. So the polarization is really interesting. We now have, the different Hellings and Downs curves for the circular polarization. And you're right that the gravitational wave background is randomly polarized, but the individual sources would be strongly polarized. I'm not sure that we haven't done any studies yet to understand at what point the polarization would be detectable over the random background. But I think that that's an important.
Boyle and Penn, and then Robert, Holden, others. The literature is filled with papers explaining how you do the polarized templates, which doubles your signal to noise when you actually template search for it. So I'm curious, why not try that? Because
yes, this, I mean, we're very interested in it, and it's definitely the next thing that we'll do. I think you're right that it's an important point, and you and I have discussed this several times, and I completely agree with you. I think that is a really interesting path forward, and I'm really looking forward to following up on those studies.
Indeed, and again, I'm happy to talk to people. Obviously, I've emailed Sarah and others about this, but I feel that either this polarization of gravitational time delays is perhaps too abstract. I'm not quite sure why it has been very little uptake. So I'm keen to talk to anyone who asks for feedback. Here's my feedback. I think it would be good cross-fertilization to try more of this.
Yes, I completely agree. I think it's a really important point, and it should definitely be there. If there's a continuous wave signal, then it's going to be polarized.
But there's 2 more raised hands. Maybe we can go to Karen next. Karen, if you want to unmute.
Yeah, thanks. Yeah, that was a really nice talk. I was confused about one slide only, which is this integral over you had an expression for the strain as a integral over the merger rate and a number of other functions. And I was just wondering, how do you estimate like things like the merger rate, for example?
Very
And
good question.
let's say given the strain, what insights can we get like on these individual components in this integral? That's it. That's my only question. Thank you.
Great, thank you. It's a high praise that you only have one question. That everything else is very clear. Right. So the way that you estimate the galaxy merger rates, you can do this in different ways. You can look at observational evidence for galaxy major mergers, and then those come from just observational papers. The way that I've done it when I've estimated the amplitude of the background is to get the merger rates from large-scale simulations, which necessarily recover what you see observationally, but it's cleaner to write down the functions that come from these merger trees than it is taking the messy observations. So there's two ways that you can get them, from simulations or from observations, but knowing that the simulations need to reproduce the observations, that they're tied together at redshift 0. And then what can you get when you make an observation? This is the rainbow plot that I showed you. I'll go over this one more time. Here we go. Whoop. Let's go back. Here we are. So this is the kind of decomposition that you can do once you have a measurement of the characteristic strain. You can make a kind of corner plot and then say, what are those masses? What's the mass of the integrated mass range that you look at that would recover this amplitude of the gravitational wave background? You can look at the minimum to maximum black hole mass. And then this number density of black hole binaries is intrinsically tied to the galaxy merger rate. And then there was a 1/1 plus z term in the numerator, and then that's, tied to the maximum redshift of the gravitational wave background. And so these are the kinds of things that you can take away from that, multiple integral equation. And when you find the amplitude of the background, you in turn decompose the background onto these different parameters, and then you can constrain them.
Actually, since we're talking about the amplitude, maybe I can sneak in a question myself. So there was a paper at the end of last year by Saldarriaga and others, also kind of comparing the measured amplitude with some estimate coming from local scaling relations and so forth. So this is the same. You also mentioned this factor of 10 enhanced amplitude relative to the supermassive black hole interpretation. Is that the same thing, or have they? Maybe you can comment on that paper.
Yes, absolutely. So their paper is a really interesting approach to modeling the gravitational wave background. I think that the major drawback from their model is that the redshift distribution just scales as z instead of 1 plus z, and that gives them very poor handling of local sources. And so if you look at the black hole mass function that's derived from their observations, you see that it peaks at redshift of 0.2. And that's crazy, right? You can't have all of the cosmic populations of supermassive black hole binaries at redshift of 0.2. So I've actually had my student working on this because I think that, having, Gabby and Matthias and Elliot join the gang is really important for pulsar timing arrays. We certainly want to look forward to more papers from them. And so what we're doing right now is we're going through and making some recommendations on how they can adjust their model so that it more easily reproduces what we see. And we look forward to working with them further in the future.
Cool, thanks. Okay.
But yeah, they assumed in order to get that result, they had to break the M sigma relation.
I see.
They used a broken power law where you have M sigma for low masses and then M sigma for high masses, and then found that the high mass one had a value that was, twice what you would expect it to be, and then over predicted the number of supermassive black hole binaries that you should see locally. But the number that they predicted is almost completely ruled out by current observations. And so there's a problem with the model, but we think that we know how to fix it, which is important.
Good. Yeah, 2 more raised hands. So there's Koichi Hirotani. Maybe you can unmute.
Yes. If you want, more number of pulsars or millisecond pulsars, gamma ray millisecond pulsars may be an alternative possibility. Well, because of the sensitivity issue, the number of gamma ray pulsars are much small compared to radio pulsars. However, they distribute isotropically and distribute nearby within a certain parsecs. So if gamma ray sensitivity further increases, I consider gamma ray millisecond pulsar also a good possibility for this study.
This is an excellent point. In fact,
Yeah.
there's already about 20% of the pulsars that we use are from the Fermilab unassociated sources. And so we use the gamma rays from Fermilab that are unassociated with anything else. And then we follow them up with the radio telescopes to see if those gamma rays come from binary pulsar systems that are millisecond pulsars. And 20% of them are. And some of them are good enough to add to pulsar timing array experiments. And so using the gamma ray aspect to add pulsars to the pulsar timing array is, very interesting, and it's very timely as well.
Because they have much greater emission solid angles compared to radio frequencies. So in the future, if sensitivity is increased, the number of nearby millisecond pulsars may further increase. Thank you very much.
Yes, you can do a gamma ray pulsar timing experiment if you wanted to. Instead of radio pulsar timing, you can do gamma ray pulsar timing. And in fact, there was a paper a few years ago that did exactly that. It's nice and it's very clean because the energies are so high, you don't have to worry about the interstellar medium and the dispersion of the radio signals. So I think it's a beautiful idea, and I hope that, my colleagues keep working on it.
Thank you very much. I did enjoy your talk.
Thank you.
Okay, next one, Kinwan. Sorry, you're still muted. You have to unmute.
Can you hear me?
Yeah.
Okay. Yeah, nice talk. And just back to the 16 nanohertz question.
Mhm.
Yeah, I really mentioned about linear polarization, but it's totally anisotropic. Can you tell? Can you tell is it isotropic or an isotropic source? This is the first question. And second question is, could it be a nice spectrum, very narrow spectrum, for example, induced by fuzzy dark matter? It's isotropic.
Okay, I'm going to go in reverse order. So the fuzzy dark matter would not have a quadrupolar effect on the pulsars like gravitational waves do. So fuzzy dark matter would cause, you have your oscillations in the galactic potential, and your pulsars are following that oscillation, and you can use that to place limits on, the mass of your dark matter particles on these, on the fuzzy dark matter particles. But that would be a dipolar signature and not a quadrupolar one. And so what we're looking at here, these are all quadrupolar signatures. So this is not evidence for fuzzy dark matter by definition. But it is an interesting way of looking at fuzzy dark matter.
At a single frequency. At that particular frequency.
So at this particular frequency, there's no evidence for something that does not have the quadrupolar shape of a gravitational wave. It would be a fundamentally different kind of signal.
Yeah, okay.
And that's not present. And then you asked if I'm going down the list, then you asked about the polarization and if it was anisotropic and could we detect this anisotropy. So right now, just this at this one frequency, there's no evidence of anisotropy. But there wouldn't be anyway. This one signal wouldn't be enough to induce anisotropy on the background. The signal is not strong enough to swamp the isotropic component in any way, shape, or form. There would be eventually anisotropy at a very high L, but we can't probe those high Ls yet. The detector isn't sensitive enough yet to get to the very high order multiple moments where you would need to go to see a kind of peak in the angular power spectrum of the background. So there's nothing yet, but it doesn't mean that we won't get there eventually.
Okay, thank you.
Okay, maybe we can take one last one from the room if there's anything from the room downstairs.
Can I speak?
Sorry, can you hear me? The mic is here.
Can I speak?
Oh, sorry, can you hear me?
Yes.
Okay, thank you for the great talk. I'm really new to this field, so sorry if I miss it. My question is like, what the level of accuracy in the astrometry, like distance or like angular resolution for each parsers are required to identify the progenitor of the gravitational wave background.
Good. So for the gravitational wave background, sorry, there's a huge echo.
I muted.
Okay,
Yeah.
thank you. For the gravitational wave background, the pulsar distance doesn't matter because only the signal at the Earth is consistently, coherently correlated in all of the pulsars. You're right in thinking that the pulsar distance matters for when the gravitational wave signal crosses the pulsar and perturbs its perturbation there, and perturbs the signal there. That's true. But when you do the cross correlation, these pulsars are all at different distances. And so those terms all disappear and only the coherent term, which is the Earth term, adds up. So for the gravitational wave background searches, we're not very concerned about the pulsar distances. For the searches for the individual signals, that's much more of an effect. And in that sense, having distances to the pulsars that are better than a gravitational wavelength are eventually going to be very important. So for nearby pulsars, that's something like a few parsecs, maybe up to 10 parsecs. And that's a big ask because pulsar distances are generally not that well known. So one of my students that I worked with at UConn, and now she's at Columbia, did an astrometric search for the pulsar companions in Gaia data, so that if we found the optical companion to the radio pulsar, we could use the Gaia parallaxes to better constrain the distances to the sources. And we did that for a few of the pulsars. So while we're not anywhere near having, parsec level or even sub-parsec level constraints for our current population of pulsars, that might be possible in the future, especially for the nearby bright pulsars, if you could do things like VLBI.
Thank you. So it should depend on the number of detected pulsars, right?
Number of sources.
Number of sources.
So if you have one, if you have one source and you know all the pulsar distances, then you gain about a factor of 2 in sensitivity and a huge orders of magnitude in localization. But if you have an infinite number of sources, then it's a stochastic limit and you don't care.
Thank you.
You're right. In the stochastic limit, the pulsar distance doesn't matter. When you have the continuous wave sources, there's been a few papers that have estimated your increase in angular resolution as a function of pulsar distance. And I'm not sure exactly what that number is. I think it's been a few years since there's been an update to that paper. It certainly gets better, but I don't remember off the top of my head exactly what that is. It's at least a factor of 2. It could be more.
1,000, because you have the wavelengths of the wave, the distance of the pulsar, so the kiloparsec to a 1 parsec, that's a factor of 1,000 angular resolution for a kiloparsec distance source. By the way, I'm just promoting our own papers on this, so I highly recommend our papers.
Yes, so you're talking about the Penn and Boyle paper.
There is a Boyle and Penn paper as well.
Yes, 2012.
Yes.
Yes, you'll forgive me. It's been a few years since I've looked at it. But you're right that having, this confusion limit that you looked at in that paper is still very much an open question. in terms of using a realistic pulsar population with their real noises. It's still very much an open question, but I think that the work that you did with Latham Boyle in that paper is really important, and we should definitely continue pushing in that direction.
Okay. Yeah, I'm sure we could get going, but I think we should let you crash. So let's thanks again, Chiara, for this wonderful talk.
Thanks, everyone. Thank you for your questions.